In this video, we will be discussing the third law of thermodynamics and refining our understanding of the concept of entropy and looking at how we can determine a change in entropy from tabulated data. The third law, as stated by Walter Nernst, is the entropy change accompanying any physical or chemical transformation approaches zero as the temperature approaches zero. Essentially, the delta S goes to zero as T goes to zero, provided all substances are in perfect order. Our working definition of the third law of thermodynamics will be the entropy of all perfect crystalline substances is zero at T equals zero, and this is 0 Kelvin. This is on an absolute scale. The key thing to keep in mind, and the reason it's underlined, is perfect. If it is perfect, that means in the crystalline structure, every single atom is in its correct location. You don't have a single atom that is not in its exact location in the repeating crystalline pattern. So the third law gives you a starting point for absolute entropy. We have a way of describing entropy as being zero. If you have zero temperature, the molecule has no thermal energy, and if it's in a perfect crystalline form, there is only one way to arrange the atoms. So the absolute entropy of a substance is the amount of energy it has due to dispersion of energy through its particles, as well as the location of atoms. So you could have, for example, this atom being out of location. That would show a slight amount of energy to get it out of position. The third law states that for a perfect crystal at absolute zero, the absolute entropy is zero. The units we will be using for entropy will be joules per mole Kelvin. Therefore, every substance that is not a perfect crystal at absolute zero will have some energy and some entropy. If one of your atoms is out of place, it does require a bit of energy to move the atom out of place. And so the molecule or your crystal substance will have a single atom out of place, and so it will have some entropy. It has more than one way of arranging itself. Therefore, the absolute entropy of a substance is always going to be positive. We cannot come up with a system that has lower entropy or lower amount of disorder than a perfect crystal with no kinetic energy. If none of the atoms are jostling about and not a single one of them is out of place, that is the maximum amount of order that you could possibly have. And so that pegs our particular entropy at its minimal value. The minimal value is going to be zero. Now, Maxwell-Boltzmann came up with an expression, and we introduced this earlier when we were first looking at entropy, where our entropy value is equal to the Boltzmann constant times the log of W, where W is the different ways of arranging our solid or system. If we're looking at a crystal, there's only one method for arranging a perfect crystal. Every single atom has to be in place. So the value for W is equal to 1. If a single atom is out of place, then if we say that we have 1 mole of atoms and only one of them is out of place, then our W value would move up to be 6.022 times 10 to the 23rd power, which is a much larger value than 1. So you would be taking the log of 6.022 times 10 to the 23rd power, which would be roughly 24. So it would be 24 times your Boltzmann constant. And so your entropy would still be a very low number. Boltzmann's constant is a very small number. So your S would still be small, but it would not be zero. Okay, so your entropy is essentially a measure of the dispersal of energy and the amount of order or disorder that the current state has. Now, if we're looking at the change in entropy, that is the difference between the entropy of our final state that we're interested in minus our initial state. The entropy change itself is favorable when the result of a process is more randomness. So when your final state has more entropy than your initial state, the change in entropy is going to be a positive. And if you remember back from our second law of thermodynamics, the entropy of the universe always goes up. So if we have a process that itself creates more entropy, that tends to lend itself to a favorable reaction. Let's look at some changes where the entropy is increased. A reaction whose products are in a more random state than the reactants would tend to lead to a higher entropy. So an example of this would be solids being more ordered than liquids, liquids being more ordered than gas. So having a solid melt gives it more entropy. Having a liquid boil, converting the liquid to a gas, creates a lot of entropy. The liquid is stuck where all the atoms have to be touching. In a gas, there are a lot of different ways of arranging gas atoms or gas molecules in the gas phase because they can occupy the entire amount of the container. So reactions that have a larger number of product molecules than reactant molecules will have a higher entropy. This is because if you produce more molecules, there are more different ways of arranging the final state than there are of arranging the initial state. If we increase the temperature, as we had seen before, that increases the entropy, because entropy can be thought of as a measure of the dispersal of energy. So if we increase the temperature, then each one of your atoms has now more different ways of arranging itself. If you're thinking about a molecule, the bonds can rotate, the bonds can vibrate, the bonds can wiggle back and forth, but it takes some energy to get the bonds to rotate, vibrate, or wiggle. So by increasing the temperature, we increase the availability of different ways of arranging the system. You could have a couple more atoms rotating than before with that additional energy. Solids disassociating into ions upon dissolving is also another form of increasing your entropy. As we saw when we were discussing the Gibbs free energy, the change in entropy is an important component for trying to determine whether a reaction is going to be spontaneous or not. So for a process where the final condition is more random than the initial condition, the change in entropy for the system is positive, and the entropy change itself is favorable for the process becoming spontaneous. Recalling again that a spontaneous process is one in which the change in entropy of the universe is positive. This follows along with the second law of thermodynamics. The entropy of the universe always increases. And if you remember from our derivation of the Gibbs free energy, the Gibbs free energy, delta G, is equal to essentially negative T times the change in entropy of the universe. So if our change in entropy of the system is positive, that tends to give us a more negative delta G value, which is our indicator for a spontaneous process. For a process where the final condition is more orderly than the initial condition, the change in entropy of the system is negative, and the entropy change is unfavorable for the process to be spontaneous. The process can still be spontaneous if it is exothermic and creates a large amount of entropy in the surroundings so that the net change in entropy is greater than zero. But the fact that the change in entropy of the system is negative reduces some of the driving force for the reaction to occur. So the change in entropy of the system is typically we're interested in chemical reactions. So this would be the change in entropy of the reaction. And as we saw when we were trying to calculate the change in enthalpy, the change in enthalpy for reaction was our products minus our reactants. Here we also have the sum of our products minus the sum of our reactants. Looking more in depth at the particulars of changing in state and the effect that it has on the entropy, when a material changes state, like going from a solid to a liquid or liquid to gas, it changes the number of microstates. If the process is going from like a solid to a gas by sublimating, then it would increase the number of microstates. It would increase the number of different ways of arranging your system. The more degrees of freedom the molecules have, the more microstates are possible. So in the case of a solid versus a gas, or a liquid versus a gas, the gas molecules are able to occupy three-dimensional space, whereas a solid and liquid, the atoms and molecules must touch each other or be very close, held together by intermolecular forces. So going from the solid to the gas, or liquid to the gas, is a large change in our entropy for our system. The term microstates is essentially just the number of ways of arranging the molecules. So the microstates themselves are the number of possible arrangements that the system has. So you can think about it as, if we're looking at a gas, this atom being up here would be a different microstate, or this atom being to the bottom left would be a different microstate from what is shown in the picture here. So giving us an example of the degree to which the entropy changes with a change in state and the effect that temperature has, if we take a solid starting out at 0 Kelvin and we initially heat it at the very beginning when it's really close to 0 Kelvin, there's a large increase in the entropy and then it levels off. It still is increasing as we increase the temperature, but it's not all that dramatic. The molecules are bouncing around, but they're still locked fairly steady in their crystalline structure. Once the solid melts, the melting process maintains the temperature, but the entropy drastically increases. The entropy goes from a low value to a much higher value as the solid melts and becomes a liquid, and the atoms and molecules are now able to slide past each other. So in the liquid form, the molecules are free to move, and so there's a lot more microstates for the system to be in. We can then continue to heat it through its liquid state. It gets hotter and hotter and hotter. This gives the molecules more and more kinetic energy. The bonds are able to bend, stretch, and rotate, and so there are more different ways of arranging the system as the temperature increases. We eventually reach the point where the intermolecular forces holding it together are not strong enough to counterbalance the kinetic energy of the molecules, and the material goes from a liquid to a gas. There is a very large change in the entropy for the transition between liquid and gas, and that's again because the gas is able to occupy three-dimensional space, and so there are a lot of different ways of arranging the gas. There's a lot of different microstates for gases to be in as compared to a liquid or a solid. You can see that there's a fairly big difference between solid and liquid, and there's a gigantic difference in entropy between a liquid and a gas. So one of the differences between the standard entropy values that you will find in a table and the enthalpy values is the reference state. In the case of the standard enthalpy, delta H formation, the enthalpy of formation, those values are relative to the elements that make up the molecules in their most stable elemental form. For entropy, because we have the third law of thermodynamics, which says that the entropy of all perfect crystals at 0 Kelvin are 0, we've established a reference state. The reference state is the particular molecule in its crystalline form as a perfect crystal at 0 Kelvin. So that is our reference state. So when you're looking at in the tables, you won't see a delta S formation. It's just S naught. The naught again is the reference state, which specifies particular concentration, 1 mole per liter, and a particular pressure, typically should be 1 bar. So what you will have is the change in entropy for a reaction is going to be equal to the entropy for your particular product times the coefficient in the balanced chemical equation. Add those up, then subtract the same thing for adding the entropy from your reactants times the particular coefficient for each one of the reactants. Add all those up, right? Take your products minus your reactants, and that will give you your change in entropy for your reaction. Remember again that although the standard enthalpy formation, delta HF, for an element is 0 kilojoules per mole in the tables, the absolute entropy at 25 degrees Celsius is always going to be a positive number. It will not be 0. And that's because the reference state, the state in which the S value, the entropy value, is 0, is at 0 Kelvin in the perfect crystalline form. So whatever you're working with is going to have more entropy than that particular value. So any value you look at in a table for entropy will always be a positive number. Looking at one of those tables, we can look to see how our entropy changes between solids, liquids, and gases. If we look at the values for our solids, we'll see that they are, in general, fairly small. As you get larger and larger molecules, right, like iron 3 chloride, right? Iron 3 chloride is a fairly large molecule, has a lot of electrons, a lot of different ways of arranging itself, and so it has a fairly high entropy. But if we're looking at something like magnesium oxide, which has a very well-defined crystalline structure, the entropy is fairly low at 298 Kelvin. If we compare that to a liquid, all of the liquids, well, almost all of the liquids are greater than almost all the solids. It's not true that all of the liquids have a greater entropy than all of the solids. For a very complicated or a larger molecule, it can have a larger entropy as a solid than a different molecule would have as a liquid. However, if we compared water as a solid to water as a liquid, the entropy for the liquid form would be far higher than the solid. So similar to the solids, as we increase the size and complexity of our molecule, the entropy gets bigger and bigger and bigger for liquids. But if we compare the value for liquids with those of gases, the value for gases is much higher than the value for our liquids. In fact, the value for the gases are almost always, at least in this table, almost all of them are greater than the liquids. The ones that are not are argon, which is a noble gas, so there are no bonds in it, and so it's a fairly simple molecule. That one is still greater than bromine, Br2, as a liquid. Hydrogen is fairly low, but if you look at hydrogen, it only has one bond. The atoms themselves that make up the bond each have only one proton and one electron each. And so hydrogen itself, H2, is a fairly simple molecule. Okay, so how do we use this? Well, let's say we're looking at the reaction for the formation of water from hydrogen and oxygen. So we have 2H2 plus O2 goes to H2O. You would look into your table, making sure that you're grabbing, just as we did with the delta H values, the appropriate values. However, because our entropy values are not relative to the elements in their most stable elemental form, our value for oxygen and hydrogen are not going to be 0. We need to look these up. So you'll take your product value multiplied by its coefficient, so it would be 2 times the value for water, which is 70 from a liquid, minus, that's all of our products, minus the sum of all your reactants, that's 2 times the value for hydrogen as a gas, plus the value for oxygen as a gas. Take your products, take the sum of your products minus the sum of your reactants, and for this process, you would get negative 326.3 joules per mole Kelvin. Now, we should expect that this will be a negative change in entropy. You can have negative values for changes in entropy. All that means is that your product has less entropy than your reactant, and this makes sense. Our reactant has 3 different gas molecules, whereas our product has 2 liquid molecules, right? So the liquids have a lot less entropy than the gases, and we have more molecules in the gas phase than we have molecules in the liquid phase. So we would expect that the reactants themselves, each individual molecule, should have more entropy than the water, and we have more of them. So our total reaction should have a negative entropy value. The amount of randomness will go down as a result of this particular process.